Hello everyone. Here in this lecture, this is basically a continuation of the previous lecture, and before the continuation, we'll like to recapitulate what we have learned before. First thing was the homogeneity of space, as is seen from the diagrams which I have prepared by now. Wherever you put the origin of the system and measure it in whatever coordinates you like. See, from this origin, this is the origin, this is the second origin, this is third origin. We are seeing the space at different points differently, but that does not matter, and that is what homogeneity calls for. It doesn't matter from where you see something, it is actually remains the same, and this is what homogeneity calls for. It is irrespective of space translation. Now we'll talk about something called isotropy. In homogeneity, we have to translate space but not rotate it. Okay, but in isotropy we are going to rotate space. We have to see the same thing from different angles. The same thing in, for example, here the northeast direction, which is said to be the Ishan cone. Similarly, in the north direction, the Uttar, the south, Dakshin, and all the other direction, wherever you see, you will see the same thing. This occurs generally in circularly shaped assemblies. So isotropy and homogeneity is the first point which we'll consider in developing Newton's cosmology, although Newton had no part in it, but it is called Newton's cosmology. For if Newton would have been a little smarter, he would have outlined and would have considered the space not to be as absolute as he said. Okay, now we will consider another structure. Here we consider a grid, and we consider that any galaxy or any point on this grid, any star you may say, is always located on a corner of a grid. You can always make such a grid that every star falls on a corner. For this you might need to sometimes thin out or sometimes space out the grid lines, but you will always find a coordinate system in which you can define all the stars to be corners in the net. Here net refers to the fisherman's net. Okay, now we'll go into the FRW equations. FRW, F for Friedman, R Robinson, Robertson, W for Walker, and N for Lemaitre, the father of Big Bang equations, which they arrived at. And I remember you that Lemaitre was a priest, a Christian, a Catholic priest, I think, and being a priest, he developed such equations. You can get great inspiration from this. Okay, priests have done some good things. Many priests, for you may take the example of George Gregor Mendel. He was also a priest, I think, or in the terms of being a junior priest, but he gave the great loss of genetics. Okay, Now we are not in biology, we are in physics here. Now see, we are considering the space, and space is filled with galaxies, and which are homogeneous and isotropic. Now consider mass here, and according to Newton's equations, which we know that any mass which is at any point, say this point, feels a gravitational pull toward the center. If we take this to be the center O, then there will be a gravitational pull towards the center, and there will be no gravitational pull from the outward any star. The outward stars will not disturb it, and every bit of force which it exerts is directed towards this O, the origin. This is the crude concept of escape velocity, where we consider that a particle escapes the gravitational pull of the Earth if the sum of its kinetic energy and its potential energy is somewhat greater than 0, or in the critical case is equals to 0. And we write this here, the same thing which we have expressed in a few lines a minute ago, is written down as half into mass into velocity square. Velocity is d dot square. Here d refers to the distance between any 2 points. Okay, the d dot square minus g into m by r. What is the distance? Distance is equals to d. So we have written d equals to 0. So this half into m into d dot square. See, d equals to a into del r, but del r never changes. The coordinate distance between 2 points, if the fisherman net is expanding or contracting whatsoever, never the coordinate changes. The star remains in this coordinate, the star remains in this coordinate. If you say, for example, we want the 2 star, the 2 star is given by here 1 2, here 1 2, this star. If the the fisherman's net expands, then the 2 star will be represented by this point. Either it expands or contracts does not vary the case. Everything remains the same. That means at least in the coordinates of the system. So we have d dot square is equals to a dot square into del r square, and this del r remains constant. Del r square, we have written it equals to, we take it to the right side, into g into m by distance. This is the potential. The potential is given by g into m by distance. What is m? This m is the m concentrated, mass concentrated over here. Here this looks like a pumpkin, but not. It is not pumpkin. Something with the not a pumpkin. It has it is a spherical geometry here. It is sphere. So the mass which is concentrated here is given by its volume into its density. Okay, m, and the distance, the d, is given into a into del r, and a into del r is the distance. Okay, we do not use the parameter t in order to avoid cluttering of the equations. See, then half into mass into a dot square, we take del r to be equals to 1. That means we take only so for example, del r equals to 1 here. You can take this del r equals to 1, or here del r equals to 1. So we are considering actually a unit sphere here for del r equals to 1. So here a unit sphere is considered. Unit sphere is considered. So del r equals to 1. So del r here to here distance is equals to 1. So we can cancel all del r's by 1, and so it will be half m a dot square equals to g into m into, what is the volume? Volume is 4 by 3 pi r cube. If I 4 by 3 pi a cube rho divided by a into del r is 1. So a here and here a cube, then a cube crosses and becomes a square. Okay, now we can cancel the mass of the small body which you have concentrated over here. Okay, you can cancel this mass, and you must say, you must say that the mass is constant. This mass is placed over here. Why don't you consider a circle like this? Rather, you are considering this distance. You must consider this distance, which is the diagonal. Okay, I understand it, but as you follow the course, you will understand that the distance between this and this is major, very small. For the main reason for that will be I think the main reason for this would be the thickness of the net which you have considered over here. Okay, you may solve the issue. This will take a little time, but let us continue with our assumptions. Okay, then half into m times a dot square is equals to u into m into 4 by 3 pi a cube rho divided by a square, and this gives us a dot square equals to 8 by 3 pi g m rho times a square. Okay, now this a square comes over here. A dot square by a square equals to 8 by 3 pi g rho, but rho is something which is not constant. Rho is the thing, is the density over here, but if it expands or contracts, the density will be reduced or it will be increased. If it expands, density will be reduced. If it contracts, density will be increased. So we'll write this in terms of some constant. Then the rho is written by mass per unit volume, the m by rho is the mass per unit volume. The unit volume is given by a cube, isn't it? Then rho is given by m by a cube. So rho is given by m by a cube. This thing is final. Okay, so a dot comes out to be root over this thing. Okay, root over this thing. Here a square and here a cube, so here only one a remains, this a remains, and when we root it over, it comes out to be this. Okay, we could have done it empirically by taking trial and error methods, but we try to do it by other methods. Let us remove everything right from here and continue with our equations. Okay, our equations give us a dot equals to root over 8 by 3 pi g m by a, pi g m by a. Okay, now what I'll do, say, I think the camera is more comfortable in the landscape mode. Is it landscape or portrait? Landscape, as it is. So what we do here, we'll take a dot by root a, gives you something of constant, root 8 by 3 pi g m. Why is this a constant? 8 by 3 pi g is a constant. This is easily comprehensible. But why is m a constant? M is the mass concentrated over here. If it contracts or it expands, the fisherman's net, it does not vary or do anything to the mass that is concentrated at a particular coordinate square or coordinate rectangle. Okay, coordinate area. So A comes out to be here root A, here root A. Okay, here root A. When this root A comes over here, then it is not over here, it is over here, root A. Okay. Sometimes it is not comfortable with chalks which are brittle. The chalks size must be a little more thicker in order that they do not break. But the chalk companies make it likewise for it to break and to use another. Okay, this is commercialization. A dot equals to here root A. This root A will come over here and A dot H. Now see root A, this is dA by dt. So take that over here. Let us call this constant. We will not give it C name, we will give it a name F times dt, where F is a constant. Okay, now we can integrate all the sides. Okay, plus constant if you like. We may not take constant. First let us solve it in this manner and later we'll have discussion. So root A dA, then it will be a to the power half, then a to the power half plus 1 is 3 by 2 divided by 3 by 2. This becomes 2 by 3. Okay, equals to F times T. Okay, so what will be the value of A? See, 2 by 3 when goes over there will become 3 by 2, and A to the power 3 by 2 times 2 by 3 is 1, then times 2 by 3. Okay, we have neglected a constant over here, you can use it. So AT, now use the parameter, is equals to F to the power 2 by 3, this into 3 by 2, this becomes a constant, say C now, and into T to the power 2 by 3. So this is the rate of expansion. This is how the universe is expanding if it constitutes matter. AT equals to C to the power 2 by 3. So AT or AT means the expansion of the universe. AT refers to the expansion of the universe. Okay, so it equals to C T to the power 2 by 3. Okay, now we know that y equals to x square. Y equals to x square. How does that go? Okay, let it be, but we know t to the power 2 by 3 goes like this. So this is how the universe is expanding. It constitutes only mass, but this is not at all the end of the case. The case starts here. Now we will consider the radiation radiation dominated universe. If instead of those mass points we have radiations, what will be the value of the expansion coefficient? Okay, now we are dealing with photons. We consider that the universe at a very early stage didn't constitute of mass, rather it constituted of something called energy. You can evaluate this in this manner, that anything which is cold enough is massive, and when it becomes hot, it starts to emit radiations, isn't it? These radiations also carry mass. The photons carry mass. So how will be the relation? Will be the relation just like this, or there will be certain difference? And we know that there will be certain difference, that it will carry this mass. Okay, the radiation will carry this mass, but it will be distributed in a awkward sense. It will be distributed somehow which is unlikely. So see, let us consider the mass which we have considered here. This mass will be replaced by energy for photons. Okay, and just to keep the equivalence, we have E equals to mc square, isn't it? Okay, equals to mc square, or this mass has an equivalent energy E in it. Okay, divided by AQ. Okay, but the energy concentrated in a particular structure. See this, what I have drawn, this rectangle or any coordinate space, is the energy concentrated in it is inversely proportional to the wavelength of the radiation. So the energy concentrated is not constant. This is something divided by the wavelength of the radiation. Then we may consider this m, but it is not the mass. M is the mass of the photons. M is the mass of the photons, but the energy concentrated is not the mass of the photons. Energy concentrated is will equate the mass given here to energy of the photons concentrated within this coordinate area. But what is the energy? The equivalence which I have stated has some ground. Please think over it and mention if there is a comment in box. So the mass concentrated here is equals to not a constant. The mass concentrated here is equivalent to an energy, but this energy is not a constant. We know the energy of a photon is given by h nu, or h c by lambda, or a constant, big constant being by lambda. So energy is equals to something constant, let it be E by lambda. Lambda means the wavelength of the radiation. Now as we expand or as we contract, as space is expanding, space is contracting, the photons which are living over here, say the photons are also expanding or contracting. So the photons are becoming of higher energy or lower energy. They are becoming redder or bluer than usual. So it is something energy we have, is denoted by energy. Let us call it F. F is a constant by lambda. Lambda is the wavelength of the radiation. Now the wavelength of the radiation is proportional to the rate of the expansion scale. If it is the expansion scale is trimmed down here up to here, then this will see, this thing will come over here, and this will be concentrated over here. If it is expanded, then it will go. It is further expanded, then this will take shape. See, this thing which I have tried to draw with analogy, let us correct it. This thing, if we expand the space over here, this space here, it is O, then the same thing will be there, but with a greater wavelength, isn't it? So but energy is inversely proportional to the wavelength, so we have a constant by wavelength by a cube. So but a cube means the lambda means wavelength. This wavelength is proportional to the size, the scale factor of the expansion. So in place of lambda, we'll write another a and give another constant over here, which will cut over, and we have another constant z over here. So it will be z by a to the power 4, isn't it? So it will be g by a to the power 4. So what we have done here, m by a cube will be g by this is not z, gravitational constant z, this is another g by a to the power 4. So there will be only a extra a term here over here. See, a square a to the power 4 square. So a will come out over here. So a dot equals to a will come out over here. The same equation will be consistent, but we have another method of writing it, and it will be root a will become a into a dot. Just follow the previous equation and you will find it why it is so. Then this will give you root 8 by 3 pi g f. This is, we consider, let us consider this g, that is not gravitational constant. Okay, so we have a dA integral is equals to integral g dt. We miss the constant always, but we can replace the constant at any time. We can replace the constant. So this gives us a square by 2 equals to zt. This gives us a equals to root 2 zt. So root 2 z, let this be h into t to the power half. So we have another thing. Now the scale at, scale factor for a completely radiation dominated universe is given by t to the power half. Before it was t to the power 2 by 3. Okay, is t to the power 2 by 3 greater or t to the power half? Actually t to the power half will be a little less cheaper, I think. So this will be t to the power half. Okay, This is the radiation dominated universe versus the matter dominated universe. Okay, and in the next lecture we'll consider another thing, which is that very interesting subject, the dark energy dominated universe, and this will give us inflation, something of an exponential increase in the expansion. So if you plot it according to time, see, we have plotted the two things differently with time, but right at the start the universe was not like that. The universe was the radiation dominated, that is photon dominated, so it was like this. Later it went on to become like this. Then we can make a connection point over here and just rub this and see, it was first like this and then like this. Okay, I'm not a good artist of a graph, but I think this will suffice if I say so the universe expanded like this. So this is the radiation dominated and this is the matter dominated universe. Radiation and then the matter. The radiation, first of all, it was all radiation, as it is considered in the Big Bang model that everything started from a singularity, so everything might be very hot and then everything might be radiation plasma, and then the matter continued to form slowly, first of all ions, then stable matter later on. And this is all for today. See you in the next video. We'll discuss about inflation and dark matter, dark energy and other things as we see. Thank you.